So we don't have any plan per se. Like what we did last time, we go over the practice assignment questions, right? If that is okay, or we can maybe do a quick summary of whatever happened in week 2, and then we can go to the practice assignment. So which of these two shall we do? Shall we do a quick summary first? Is that fine?
Yeah, that's better. Maybe in between, if I have any doubts, I can ask while you're summarizing.
Okay. Okay. Right. So yeah. So I'll just try to point or list down those topics that are like most important in this week. So we start off with the difference between this immediate RL and full RL, right? So we saw immediate RL or the bandit problem in the first week, and now we are going to move to the setting of full reinforcement learning. So let's quickly try to draw differences and parallels between these two. So in immediate RL, you don't really have a notion of state. There's only one state, right? So there's only one situation, and
Action.
one situation, right? So you have one situation, and in the actions, yeah. So you have multiple actions, right? So you have multiple actions, and rewards are immediate, in the sense that every time you take an action, you get a reward, and they're also tied to a specific action. Right? So there's no problem of assigning credit to an action, because you know that the reward that you get is tied to the action that was taken prior to getting that reward. So rewards are immediate, and they're very it's a one-to-one mapping between the rewards and actions. What else do we have in immediate RL? Your goal is to take one of these goals is to find the best term, right? So that is one of the goals. Of course, there are other goals we could define. So find the best term. Eventually, it's one of the goals that we could strive to. Right? So find the best term eventually. This is the immediate RL problem, and we contrast this with the full RL problem in the second week, where we say that we have multiple states. Right? We have multiple states. There is no longer a single state, so you have multiple situations that the agent could be presented with, and you could have multiple actions. This is kind of similar to what we had in the immediate RL setup, but with the difference that they need not
Every
be
state
necessary.
has every
Yeah,
state
sorry.
has different actions and different rewards,
Right. Yeah.
dependent.
Right. So you could have different actions in different states, right? So you could have different. They don't need to be necessarily the same across the states. And the rewards. So here the immediate RL, the immediate rewards here they are delayed, right? So they are delayed rewards. They need not be tied to a specific action. I mean, the need not be tied to the okay, we put it as the current action, right? So the action that you just took, the reward may not be because of that particular action. It could be delayed, right? So it's also we have seen in this week, and the goal is not just to find the best action in a particular state, but to you know find the best way of behaving, right? So the best way of behaving so that you maximize the cumulative reward. Here you are just looking at one action to choose from multiple actions. Here slightly more complicated. You have to choose the best way of behaving. So when we
What,
talk about any
what
questions?
do you mean by behaving? Are we looking at sequence of operations to we optimize our like overall
Yeah,
reward?
right. Yeah. So we should make this idea of behavior clear. So the policy is what determines the behavior, right? So what action to choose
Maybe
in
objective.
a given state, right? In a state. So how do I behave from a given state, or what action to choose in a given state. So the goal is to find in some sense, the best policy. So that best policy will come in week 3. So how to define what is a good policy and all that, we'll look at it in week 3. But as far as week 2 contents are concerned, we are looking at we are trying to find a way to behave optimally so that in the long run I get as much reward as I can. Right, so that is the goal. Here also there is a policy, right? So here also we could have the notion of a policy. Policy is what action to choose, right? That's all. So the policy here is just what action to choose eventually, right? At the as t tends to infinity, what arm should I keep picking? Here the policy on the full RL side, since there are multiple states, you need to know how to behave in each state, right? So that is that's the overall difference between immediate RL and full RL. Okay, so this is one thing that happens in week 2. The other thing that I wanted to just mention briefly is the idea of how do you, so we see that we formulate this whole problem as a Markov decision process, right? So we formulate it as a Markov decision process. So I just want to build up to that. This is something I watched in one of the lectures by a prof in Stanford. So I'll maybe add a link to that later. So she talks about 3 processes, right? So there are actually 3 processes that lead to this whole idea of Markov decision process. One is called a Markov process. Another is called a Markov reward process, right? It's called a Markov reward process. And the third thing is the Markov decision process. So these 3 are kind of very interesting because in the case of Markov decision process, you have states and you have to choose actions from those states and you will get rewarded based on what actions you choose. Whereas in the case of Markov reward process, you don't have the notion of actions. You just have states and then you get rewarded based on which state you are in. And the Markov process, plain Markov process, is even more simpler, right? So you just have states and you just transition from one state to the another, one state to another based on some transition probabilities, right? So it's kind of interesting to look at 3 different processes.
I mean, in Markov reward, are we saying that my probability is conditioned on my reward?
In which process?
Markov reward process.
In Markov reward process, the next state and the reward depends on your current state. There is no notion of action, right? So let me write down, see the distribution, the distributions that you are interested in each of these cases. So in the case of a Markov process, you will just have this notion of P of x prime given x, right? So you'll have these transition probabilities only. So if you are in a state, what is the probability that you will visit this next state, right? You will transition to this next state. There's no notion of action in the Markov process. In the case of the Markov reward process, what happens is there is no notion of action. So you are in a current state, yes, you are going to transition to the next state, but you're also going to observe some reward, right? You'll be rewarded with some value R in the future, right? So this is the Markov reward process. The MDP is the most comprehensive of all of them, right? Where you are in a status and you have agency, right? You can act. So you can act, you choose an action A, and that will take you to S prime, and along the way you will get a reward R. Right? So these are 3 increasingly complicated, complex processes, and you can basically look at this as containing the other 2, right? So for example, if you have an MDP in which whatever action you take is irrelevant for the next state, right? Or for the transition, that will break down to, or that will degenerate into a Markov reward process, right? So assume that you have an MDP where no matter what action you choose, that has no effect on the next state and the reward. So that will collapse into a Markov reward process. Likewise, if you think about a Markov reward,
But at second also, like we are optimizing for choosing an action that maximizes my reward, right?
In which one? This one?
Yeah.
Here, there's no notion of action, right? So
But
the process.
while transition, you are calculating the reward. That's some kind of analogy to choose the state, right? Then.
So here you don't have any agency, right? You don't have any control over how to behave. So you are in a state, yes, and whether you like it or not, you are going to transition to the next state S prime with some reward or with some probability, right? So you don't have control over. So you are like kind of helpless in this case, right? So the notion of action is absent.
Okay, so here based on action, your S prime might change.
Yeah, here based on action, your next state and reward are conditioned on both the current state and
Okay.
on the action you choose.
Got it. Yeah. Thank
Okay.
you.
So here's a it's a very quick example of the transition graph. Sir has done it, but let's maybe quickly do it. So assume that there are only two states in an MDP, right? S1, S2 are two states that you have in your MDP, and or let's start from the Markov process, right? So how will a Markov process look? You will have two states, and you will just have transitions between these two states. Okay, so this is S2, not S1. This is S2. So you could have S1 to S2, and you could have S2 to S1, and of course you could also have S1 to S1, right? So you could have self loops, right? And just add one self loop, and this should be kind of should make sense, right? So this is likewise we'll have something for S2, right? And each one of these transitions will have some probability, so you can represent the whole thing using what is called a transition matrix, right? So you can call that P. So if you look at it, it will be something like this. Say one, we have state one here, state two here, state one, state two here. There's a say probability of 0.2 that if you are in state one, you come back to state one, and a 0.8 probability that if you are in state one, you go to state two. Right? And maybe for S2, you could have it as a 0.4, 0.6, right? Yeah, as you can see.
Oh, you don't have self loop, right?
Or all right, yeah. So that's correct. Okay. So according to this figure that we have drawn, this has to be 1 and 0, right? You're right. So this is a transition matrix, right? So this is what a Markov process will look like. And if you have a Markov reward process, then what you will do is you will also add rewards along the way, right? So you'll say that if transition is to itself is 0.2, it will happen with a probability of 0.2. Maybe the reward it will get is say 2, right? And likewise you'll have something on each arrow, right? That will be a Markov reward process. When will this become an MDP? It will become an MDP when you don't have these direct transitions to states, but instead you have an action A, let's say A1. From each state you can do and perform say 2 actions. So from S1 you perform an action A1 that takes you to S2 or to S1. Okay, along the way you get some reward. So like I'll just do this for one transition. So S1 to A1, and A1, the environment responds by taking you back to S1, say with probability 0.3, and you get a reward of say 3, right? So this is corresponding to this transition. What will this be? What should this be? A1 to S2, 0.7, right? So it has to transition to S2 with 0.7 probability. Reward could be, let's say, 0.3, right? So this is what an MDP will look like. Of course, I have not completed it. You could have multiple actions from S1 and totally different set of actions from S2. Okay, so that is roughly what an MDP, the basics of MDP. What else is there?
Can we we can condition this on sequence of actions, right? Let's say maybe on a state in a time step 2. Let's say my agent is took an action of something. my future reward can be conditioned on whole everything, right?
Right. So that's where the Markov property comes in, right? So you have, so this is, let's make this st plus 1. Let's say this is st plus 1, and this is rt plus 1, right? So this is the future in some sense. This is the future. And what we are saying is that this is the probability that if you are in state st and you take action at, you transition to st plus 1 rt plus 1, right? So the nice thing about an MPP is that the state is Markov, right? So which means the probability of st plus 1 rt plus 1 given st at is equal to the entire sequence, right? If you instead of st
T
at,
minus 1. Yeah.
yeah, you replace the whole thing, st minus 1, at minus 1, and of course also the rt minus 1, right? So rt minus 1, whole thing. So
Okay.
that's
Okay. Yeah.
that's what. So the all three are Markov. By the in the all the common theme among all three processes here is that they're all the states are Markov, right? In each of these processes, the main theme is that if you know the current state, you know what where you will transition to. I mean, you may not know exactly where you transition to, but at least probabilistically you will know, where you will go. So that's the Markov uh, assumption in play. Okay, so we have seen immediate RL versus full RL, the rough outline of MDPs, and the third thing that was discussed in this week was the idea of returns, right? So what is a return in a Markov decision process? So let me delete this from this. Okay, so the idea of return is nothing but sum of rewards. Okay, in some sense, sum of reward, right? So it's RP plus 1. That's the way we do it, right? So reward for taking action AT in time step ST is RT plus 1. So for a task that is episodic in nature, where say something like playing tic-tac-toe or playing a game of chess, where the experience naturally breaks down into a sequence of episodes, you can go ahead and simply write the return as the sum of the rewards, right? So where you finally end up with some terminal state capital T, right? So assume that in time step capital T, you end up with some reward RT, and that's the end of the episode, right? So then you can write down the return like this. So this is one way of writing the return, but in general, what happens is we could also have tasks which are not episodic in nature, which keep continuing. Okay, so there, what we do is we add this discounting factor called gamma, right? So the first reward is RT plus 1, but then for future time steps, you discount it or you just keep multiplying it by a factor of gamma. So this will become gamma RT plus 2, gamma square RT plus 3, right? So on and so forth. Right? It'll keep going on and on. One of the reasons for doing it is mathematically, at least, to keep this sum bounded. Right? So if your task is continuing in the sense that it keeps going on and on without any notion of final end state, if the trajectory keeps going on till infinity, what will happen is that your sum will become unbounded. So one way of keeping it bounded is to define this kind of return, okay, and that will make sure that it's bounded. It is one reason, but not the only reason.
I have a doubt. Like, how do we? I mean, are we for RT plus 2? If we don't explore it on a continuous, let's say on a solution space, we don't know about it, right? Then how do we like bound it?
So we are saying that the return will be bounded, right? The return GT will be bounded if you do this. If you define
No,
this
no.
kind
Let's
of
say if I want RT plus 2, I need to go there, right, to do some action.
yeah. So yeah, maybe I missed this part. So what happens is this is the return when you follow some policy phi, right? So you are following some policy phi, meaning let's say, so let's make this explicit. Let's say you start from state f0 Okay, you start from S0 and then you behave according to policy pi, right? So pi is going to give you, assume that it's a deterministic policy, meaning in each state you can only pick one action, right? So if you're in S0, then you choose the action pi of S0. Okay, because of that you get a reward R1, right? So that R, this is R, like, so this will be G0. Let's take the case of G0. So this will be what? This will be R1, R2. So how do you get R2 in this case? You get R2 by continuing to behave according to this policy pi, right? So you get reward R1, you transition to S1. Now from S1, what do? You again need to choose an action, right? So the action you choose is pi of S1, right? You are behaving according to this policy pi. So once you choose S1, you will get R2, right? You will get R2 and you will transition to S2. So this will happen kind of like simultaneously, right? So you will transition to the next state, and along the way you will get R2. Was that your question?
Yeah, that is a question. But at this point, we are exhaustively searching, right?
So we are okay. We have not yet mentioned how we search for good policies. Okay, how do we arrive at a good policy? Currently, we are only at the state of behaving according to some policy pi, right? So we have that's a valid question. How do we search for good actions in a particular state? We'll come to that starting from week 3 when we actually solve for the markout decision process. When we try to solve for the MDP, we will try to address the question of how to search for the best action in a particular state and then behave accordingly.
Okay.
Okay, currently we are just mentioning if you have some behavior that is given to you in the form of this policy pi, what happens, right? That is
We'll
all.
follow that. Yeah.
Okay, so this is the notion of return. So the return is nothing but a way to give you a sense of what is the long-term cumulative reward that you will end up getting. Okay, so what is the long-term reward that you'll end up getting? So gamma, this factor gamma is an important one. Gamma is between 0 and 1. Okay, 0 less than or equal to gamma less than 1. Of course, you could choose one, in which case you can choose one when your task is episodic. That's fine. But generally, for a combined framework, we choose gamma to lie in this range. Okay, so this is the notion of return. Once you have the notion of a return, the next thing that we have looked at in this week is the idea of a value function. Okay, so the idea of a value function, we call this v pi of s, right? So recall that in the lectures on bandits, right? What we computed, this q function we computed, right? So we computed the expected reward when you pull a particular arm, right? So what was that? It's actually telling you how good a particular action is. Okay, so what the value function tells is, at least this particular quantity is how good this policy is when you, so how good the policy, right? It's actually trying to evaluate a policy. Okay, it's giving you a quantitative measure of how good the policy is. So if you start in status and you behave according to this policy, this is the expected return that you will get in the long run. Okay, so do you all understand the notion of value function? Because that's like one of the most important.
Value function is basically a deal breaker, right? Like it's one state. Can I say that way?
Sorry, can you please repeat that?
Let's say value function acts as a more of a optimizer in a way, like take the best action. This defines that.
Okay, so the value function will help us arrive at that situation, right? Where we can find out what is the optimal way of behaving. As by itself, it may not give us the best way of acting. What it will give you is an objective evaluation of the policy, right? How good is my policy? So if you take two value functions, say v pi 1 corresponding to policy 1 and v pi 2 corresponding to policy 2, right? You have two value functions. Now you can make you can start judging these two policies based on their value function. So, right. So I hope this is what you are referring to when you say that it's a deal breaker, right? Using the value functions for two different policies, in a way, I can compare the policies, right? So I can do that
Again, I
because
mean, within
yeah,
comparison and while I'm transitioning from states, does value function comes into the picture?
while you're transitioning from the states, the value function doesn't come into the picture because the only thing that matters is what is your policy and what is the dynamics of the environment, right? So that's the only thing that matters for giving you this trajectory, right? The value function is your estimate of the goodness of a policy, right? It's only telling it's not a part of uh, the agent's behavior or the environment's response to your behavior, right? So it's purely a metric for you to evaluate policies. Okay, of course,
Okay.
the value function will help you arrive at better policies. We'll see that in the next week, but it won't directly tell you how to behave, or it won't impact the dynamics of the environment, right? So that is totally separate.
So value functions will give me better policies. Better policies
So
will define the rewards.
so using the value functions, you can reach better policies. I mean, not directly. So there
Mhm.
are algorithms that will make use of the value function to reach increasingly better policies, right? This is something that's going to be covered in the next week,
Okay.
right? So why is this a measure of a good policy? It's because of the way it's defined. So let's quickly look at the definition. It's the expectation of the return, whatever we have written down here, right? The cumulative discounted reward. So this is what? This is the cumulative reward. If gamma equal to 1 is just the sum of rewards, right? It's the cumulative reward. But if gamma is not equal to 1, which is typically the case for continuing tasks, this is the cumulative discounted reward, right? So that is what the return is. So this is the expected value of the return starting from status, okay? And the expectation is taken over two things. It's taken over the policy pi and also over the environment, right? So it's taken over the policy pi and also implicitly over the environment, because if you behave according to policy pi, the environment is going to again come in and add its own randomness, right? So the expectation has to be
Mhm.
taken over both of them. Any questions so far at this stage? Okay, right. So that's the value function. I don't think we have covered anything more than the definition of this expectation. Have we seen anything more in this week? I don't think so.
No.
Right. So yeah, we stop at defining v pi of s as this
Mhm.
expectation of the return given a status. I think we also define the action value function, right? Have we defined that also in this week?
Yeah, action value again.
Yeah, we have defined, right? So let me just quickly go ahead and make that down. So the
That is
action,
coming from MDP, right? Then,
sorry.
I mean, action value is somewhat similar to whatever you earlier said about markout decision process. Like my
So
action is defining.
right. So all these are a part of the MDP, right? So yes,
Okay.
the states, actions, rewards, along with the transition probabilities, make up the MDP. And what we are trying to do is we are trying to add a few more constructs on top of the MDP. So the value function, the state, this is called the state value function, right? So this is the state state value function.
Mhm.
One second, it got stuck. Something got stuck here. Yeah. So this is the state value function, and this is the action value function. So this is the action value function. So these are two value functions that we need to be aware of. And this is again expectation over a policy pi, but the difference here is that To start from status, take action A, and then you behave according to this policy pi. Right? So that's the main difference between these two value functions. You don't directly start behaving according to policy pi. You start from the state, take a particular action A, that will transition you to some other state with some reward, and from there on you behave according to pi. Okay, so that's the main difference between these two value functions. Right, so that is mainly what we had for this week. Now, shall we go ahead and discuss these practice assignment questions? Any questions
Sure.
about? Okay, yeah, so we'll do that. Pretty quickly we can go through, not many are there. So this is the first question. I'll just paste the okay, let me. Yeah, sure. So just give me a second. I'll have to share my window. That's easier. Okay, so yeah, so this is the it's visible, right?
Yeah.
Yeah, so this is the first question. Now we have this example from the lectures. Find the undiscounted return for each of the following trajectories, right? So we have to start from here, and first trajectories, you move left, right? So what do you think is the return for this case? You
4.
move 4, right? So it's 4. If you move left and you move right,
That's 2.
2, right? And right, left is 0, right is 2. So it's like simple question, 4202. Right, so this is the second one. Right, so you have a robot that can take 4 actions, and someone is watching this robot, and every time the robot takes one action, you record that action. Say, for example, at time t equal to 0, when the observer starts his stopwatch or his timer, the action is left. Okay, 3 seconds later, the action taken by the robot is right, and after 10 seconds, it's front, so on. Right, so 5 actions are there. So what notation should you use to define these actions? So should it be
So
A0?
let's say, yeah. What if I add no action as a valid action here?
You could add, right? So you could add no action.
At that point, option 2 will be correct, right?
At
Because
that point, yeah.
taking
Well, in that becomes a
time
bit
steps,
tricky, right? If you add no action as an option, that means
that is an action. Not reacting is an action. So it will be for every time step counted.
it'll
T1,
be
T2,
a,
T3, T4.
okay. That will be very tricky to model, right? Because you have infinite. I mean, it's like every second, not even every second, right? I mean, every millisecond, microsecond, you are not acting. Right? So very sparse actions are only there. Right? Very sparse, non-trivial actions are only there. So may not be the right thing to model that as an action, because that your whole system will break down if you try to model that as an action, right? Because you have to keep on saying not action, not acting, not acting, not acting, and
I
so
mean, it's like from self loops in Markov model, right? I mean, coming into the same state after the earlier state, if that is same, can also be valid, right, in Markov chains.
yeah, but there no action is there, right? So here you have here also you could act and come back to the same state, right? So there are some actions which you could do. For example, if you take this grid world, which we see here, right? So as this world, you could, if you try to move up here, you will not be able to move. So you'll come back to the same state, right? So You
I mean,
can
at that point, I believe the policy will be changed, right? The valid actions is only down because everything
no,
is blocked. Isn't
not
that?
necessary, right? So the policy is uh, the transition is defined in such a way that if you try to make a move that takes you off the grid, you will come back to the same state, right? So that is, you have a valid action there also. Only that the
Okay.
environment responds by pushing you back to the same state.
Same state. Okay.
Okay, so if you assume that there are only four actions available, then
Hmm.
which of these two is correct?
I mean, first one. I mean, based on action, I basically.
Okay, yeah, right. So the first one, because you the notion of time in RL is not the time that has elapsed, but
Mhm.
the decision steps, right? How many decisions am I making? I'm making this robot here is making only 5 decisions. So we have to index the actions based on that and not based on how much time has elapsed while taking these actions, right? So that is the question there. Okay, so that is one problem. 3 and 4, the basic idea is you are given these rewards, okay, for a task which is continuing with gamma equal to 0.9, and you have to find what is the return, right? So I have already written down the answers here. Uh, so maybe let's copy this and just quickly go over this. So R1 is -2, R2 is 5, R3 is 4, R4 is 2, and R5 is 1. Okay, R3 for all other P is equal to 0 for P greater than or equal to 6, right? So we have to find G5. So what do you think G5 is going to be? The return starting from state at time step 5, and then
R6.
it will be R6, right? It will be R6 plus
Mhm.
gamma R7,
Gamma R7
right?
plus
And so on
gamma
and so
square.
forth.
Yeah, and so on.
Right? What will this be?
0.
This will be 0, right?
And
Essentially,
given if RT is full.
right? So this will be 0, as you said. So this G5. Now, what about G0? G0,
0.9 into minus 2 in that way.
right. So it will be this whole thing, right? It will be R1 plus gamma
Gamma
R2 plus gamma square,
till R5.
yeah, plus gamma gamma cube R4 plus gamma power 5, sorry, 4 R5, right? So one way to compute is by substituting all the rewards, plugging in the value of gamma, so you'll get the final answer, which is say 7.85 in this case. Alternatively, what you could do is you could,
Geometric proof.
yeah, right. Well, what, so this is the recursive way, right? So, for example, if you look at
Mhm.
D0, it's what? It's R1 plus, you take gamma common, it is actually D1. Do you see that it's
Hmm.
D1, right? Because
Yeah.
R2 is nothing, R2 plus gamma R3 plus gamma,
Gamma R3.
right? So that is just G1. Likewise, you could write V1 as R2
R2 plus
plus gamma
gamma G2.
G2, right? So you could do this. Now you could continue in this way, right? And for each step, you can write this recursive procedure. So one way to do this is to start with G5. Okay? G5 anyway we know 0. So first go and compute G4. G4 is R5 plus uh, gamma G5, right? So now you get you can compute G4. Once you know G4, compute G3. G3 is R4 plus gamma G4, right? Once you know G3, you can compute G2, so on. And then you can finally come to G0, right? That's another way of computing it. Basically, you can choose
Mhm.
whichever is more convenient. Okay, so that is
I think if doing with pen and paper, first one is easy.
right. Yeah. Okay, Okay, so that is 3 and 4. Question 5 is just asking you what does this Q pi mean? So Q pi means what? It's the expected return when you start from status, you take action A
Taking
and then you
action.
follow policy pi, right? So that is what Q pi is. Expected return starting from status and following policy pi will be just the state value function, which is V pi of S, right? There's no action involved, so this is V pi of S. The return starting from status equal to 1.5 in some episode, that is wrong because the value functions are expectations, right? They are not just returns, they are actually expectation of the return, right? So simply adding the return is not correct. Same for this, right? Simply stating that it is the return is wrong. It's the expectation of the return. Okay, so that is that. Now, which of the following statements are true regarding the state and action value functions for a stochastic policy pi? Okay, so any questions in this? This is just the definition basically. So you know the state action value function, right? So the action value function. Now this is just how probable it is that you will choose action A from status. That is the policy, right? What is the probability that you will choose particular action from a status? Okay, so if you just compute this expectation, you will end up with the the expected return starting from status, which is what V pi of S is. Okay, any questions in this particular problem?
I mean, because we are accumulating over A, the action might not differ, right? Because we are expecting everything.
Right. So we are taking the expectation over all, the policy
All
pi,
the
right?
actions.
Yeah. So sigma pi A given is, so Q pi S comma A is, what is the return? Sorry, what is the expected return if
Based
I
on
start?
action.
Yeah, if I start
Hmm.
from S and act as if I start from S, take action A, and then behave according to policy pi. So that behaving according to policy pi after S comma A is taken care of. Now, what is the probability that you will behave according to action? Uh, you will take action A in the first place. That is given by pi of A given S. Right. So this is
I mean,
just
is this not a state value function? It is,
that's
right?
correct. Yeah, this is the state value function, but this is giving us a relationship between the state value function and the action value function.
Action. Action. Okay.
Okay, so maybe I'll just spend some time on this. So what we are doing is we need what is the value starting from status and behaving according to policy pi. Now the way we split this is we first choose an action A. How do we choose an action A? Using a policy pi. With this probability we can choose an action A. So once you have chosen an action A from status, what is the value if you behave according to policy pi, that is given by Q pi, right? Because you have already taken an action A in status, right? Therefore, that part is taken care of by this summation. Once you have taken action A in status, what will be your value? That is given by Q pi of S comma I, right? So it's like one step you act and then you behave according to pi. That is the split that is given here, right? So this is the first option. The second option is incorrect. It doesn't make sense to have this probability here anyway. Why do you think the last option is wrong? V pi of S equal to Q pi of S comma pi of S. Any ideas?
Well,
So pi of S is actually, what is pi of S? Can
current
we
state, current policy at status.
right? What action to choose from status? But we have been given this fact that policy is stochastic, right?
Okay.
So since it's stochastic, you can't just write pi of s. You can only get a probability distribution over the actions starting from state s, right? So this is therefore incorrect. Option C is correct because it's the definition of the state value function again, right? So you're fixing s, but then you have liberty to act according to policy pi, right? Therefore, capital AT here is, you treat it as a random variable.
All the actions.
Yeah, right. So that's what 6 is about. 7 is basically a problem discussed in the lectures. So we are asked, what is the value of a plus b plus c plus d? You have two states and you have two actions from each state, and these are the transition probabilities. Some of them are given here. So any ideas what a could be here?
1.
Okay.
Sorry, 0.25.
Yeah, this is 0.25, right? So if you start from state hot and you advertise, you can go to hot again with 0.75 probability, and 0.25 probability you will go to state cold. Now, so what is C going to be?
One. I mean, only a 1 out. Sorry, 0.3.
0.3, right? Yeah. So if you don't
Diagram
do
is bit
research, then 70% of the time you go to cold, 30% of the time you go to hot, right? So this is 0.3. B and D, right? So what do you think B and D could be? Okay, so can we determine B and D explicitly, or can we say something about B and D together?
They can be 1.
Okay, right. So
They will be 1.
Right, B plus D will
Yeah.
be 1. Right, so B plus D has to be 1 because from research action you have to go to one of these two states, and probability of going there has to be 1 together. Right, so if you add all of them together, B plus D is 1, A is 0.25, this is 0.3, so it will come to 1.55. Right, so it's just completing the transition graph. Problem 8 we just saw, right? The whole idea of Markov state is the probability of the future is independent of the history, okay, independent of your past, given your current present, right? Given the present. So the probability of where you will be in the future is independent of the overall history or your past, given the present, right? So if you know what the present is, you know what the future is going to turn out like, and that doesn't depend on your history, right, or on your past. So that's essentially the Markov property, and that's what this problem is about.
What is PR here?
Probability, right? So PR is probability.
Okay.
Okay, that is 8. 9 is a bit kind of involved in terms of computation. What is next? Yeah, so maybe we'll come back to 9 later. Is anyone else there? 2, 3 of you are there. Okay. So we'll finish this grid world. This is easier to, right? So we go to this, we paste it here. Okay, so this is the grid world, right? So this is a policy in this grid world. So anywhere you are, this policy here is the way to behave, right? If you are in a given state, what should you do? So for example, if you are in this state, the policy is telling you to go up, so you'll end up in this state. Okay. So why will you end up in this state? It's because there's a term that's given here. Assume that all the transitions in the environment are deterministic. That means that if you decide to go up, you will end up going up, right? You won't magically go to some other state, right? Because it's deterministic, you will end up going there. So that's what it means to say that the transitions are deterministic. So the reward is 1 on reaching the goal. Okay, for all other time steps, reward is 0 for all other states, right? So you have to and this has some gamma, right? This gamma is equal to 0.9. Let's say that term gamma is equal to 0.9. So this is episodic. So that there is a notion of episode, right? If you keep going and then you reach the goal, that defines one episode, and then you again start from some state, and then you go reach the goal. That is another episode, right? So it is episodic, but you also have a gamma associated with it, right? So that's the catch you need to be aware of. Okay, in this situation, what is the return starting from the bottom left state and following policy pi? So that's what is asked. So you start from the state and you have to compute the return when you follow this policy. So let's just follow the policy and see where it takes us. So you start from here. So you go right, you're asked to go right. Then you go up, you go left, you go up, you again go up, you go right, right, you go down, go right, up, up, and you reach the goal, right? So how many time steps do you think it took us?
12.
12, right? So took us
Gamma
12
power
times.
11 into 1. Can I say that?
Yeah, exactly. Right, that's correct. So V0, the return is what? It's R1 plus gamma R2 plus dot 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 plus gamma R12, right?
12. Gamma power 11 or 12.
Oh, sorry. Yeah, you are right. This is gamma power 11 R12. Right, since R1 to R11 are 0, they are 0 because there is, by definition of the problem as given in the problem, R12 is 1, right? So gamma power 11 into 1, so this is gamma power 11. So if you compute 0.9 power 11, it will turn out to be roughly 0.314. Okay, so that is the return. So what is V pi of 0? Or rather, what is the value function for this state, this particular state? If you start from the state and behave
As
according to
we don't have more choices, it will be deterministic, right? If we have more choices, that will be cumulative expectation.
right.
Can we assume?
Yeah, that's exactly the point. So if we don't have a stochastic policy, or if the environment is deterministic and the policy is also deterministic, in this case, the expected return will just be equal to the return, right? Because everything is deterministic. So if you just compute one return for some episode starting from the status, you will end up with the same trajectory in every episode. Whatever episode you can think of, it's identical, right? So the return will always be gamma power 11, and because of that, what we need e pi of 0, right? So that's nothing but e pi of v0 given it's t equal to 0. This will also be gamma power 11 because there's no probability involved anywhere here, or everything is deterministic. So that's why we have the same answer. Final question is this one. Okay, so the question is kind of big. I'll just explain it here. Okay, so assume that you have two tasks. You have task 1 and you have task 2. Okay, now both are identical. Both are identical, but for the rewards, right? So if you receive a reward of RT by performing an action AT in state ST, right, or rather RT plus 1, okay, uh, let's call this state the world 1, right? I'm calling this world 1. This is world 2, right? Now the reward that you obtain in world 2 is what? RT plus 1 in world 1 plus C. Okay, this is the relationship between these two worlds or these two tasks, right? Everything is identical. So if you take an action in this in a particular state in T1 and you take the same action in T2, you will go to the same state in both the worlds. Only thing is that rewards for this world will be C more than the rewards that are present in this particular grid world or whatever you want to think. Okay, so this is the situation. Now what we're asked is, you have the same policy for both the tasks. What is the value function for T2 in terms of T1? That's what is asked. So you have some value function called V pi for 1. Okay, and that's what we have, V pi 1 of S. We have V pi 2 of S, right? So what are what is the relationship between these two value functions? Any idea? Do you have any idea how to?
Again, recursive.
Right.
That will
So
be
that is one thing we could do, right? The other thing is we could just look at the definition of these two. So this is what this is pi of dt equal to, so given st equal to s, right? So this is the returning state 2, right? Sorry, or in task 2, right? This is what this is the expectation of the return in state 1, or rather in task 1, starting from the same status, right? Now this means that if we can somehow relate GT2 and GT1, we are done, right? So if we can relate GT2 and GT1, we are done. So what is GT2? GT2 is same RT plus 1 in world 1, sorry, in world 2,
let's see.
right? So plus gamma times RT plus 2, again in the second world, okay, plus dot dot dot, right? Now if you think about this, we know this, right? We know this. So RT plus 1 in the second world is going to be what?
30 plus 1 in world 1 plus C.
Yeah, RT plus 1 in world 1 plus C, right? So this is the first term. What about the second term? Will be RT plus 2 in world 1 plus C again, right? Right. So this will keep repeating. Now let me
GT in world 1 plus
correct. This is GT in world 1
gamma.
plus.
I mean, it will be gamma C whole square. I mean, it goes on.
Yeah. So this
C
will be
gamma
just.
plus C is gamma C square gamma. Yeah.
Yeah. You're right. So you take the C out and then you'll keep adding this gamma square, right? So this is nothing but a this is nothing but a geometric series, right? Whatever is there inside the bracket, right? So this is just a geometric series. So this becomes dt in world 1 plus C by 1 minus gamma, right? This gamma is between 0 and 1. So the sum of the infinite geometric series is 1 by 1 minus gamma. So you end up with this, right?
Okay. Yeah.
Now I can, since the C by 1 minus gamma is a constant, I can pull that out of the expectation and replace this as e pi of dt1 given st equal to s plus
C by
1 minus gamma. So what is this expectation going to be? This expectation is the value function in world 1, right? So it's the value function in world 1 of s plus c by 1 minus gamma,
constant.
right? So that is what we have here. So it's e pi of s plus c by 1 minus gamma. So if you have a continuing task such as this, and you add a constant amount of reward to every particular situation, right? Or if you just add a constant reward, what will happen is the value function will get shifted, right? It will get shifted, but it will shifted by a constant. So that constant is c by 1 minus gamma. Okay, so that is all I had. Any other questions?
Sir, could you go to question number 5 and practice assignment?
Yes, yeah.
Sir, little I had doubt with what is policy. So policy is what, like when I'm at particular status, does it give me the probability of all possible action, like taking all possible action at that particular state is. Does it?
Yes, yeah. So if you have this, if you take this case of, let's say the grid world, right? Now, okay, so let us take a smallish looking grid world. We increase this so that you have only 9 states, right? So what? Let's number the states. So if I number them as say 0, this is 1, 2, this is 3, 4, 5, 6, 7, 8. Okay, so this is 0, this is 1, this is 2, this is 3. Sorry for this. I'll just complete this for completeness. If I mark this, so this is 6, 7, and 8, right? So these are 8 states. Now, when I say pi of 4, okay, so it's actually pi of a given s, right? Now there are 4 possible actions from state 4 to go left or north, south, east, west, right? So so what the policy is telling you is give you a probability distribution over the actions, right? So you could have something like north, right? What is the probability that I will take the action north from state 4? Could be say 0.2, right? So let's define the complete policy for the state. So north is say 0.2, east is maybe 0.6, and the west could be 0.1. What that leaves us with south? What could south be? So south has to be 0.1, right?
Yes, yes.
So this is a policy, right? This is policy for one state. So policy is defined over all states, right? Every single state there will be a value for the policy, and typically it's stochastic, meaning it will give you a probability distribution over the actions that you can take start given that status.
Okay, okay. So it is nowhere like related to reward. It just like gives a route, possible routes from at that particular state.
Yeah,
Right.
yeah. So the policy is exclusively tied to your agent, right? So there are two things, right? Agent and there is environment. So
Yes.
the agent controls the policy, right? Or the agent can specify a policy and it can act according to that. So from 4, the state 4, the agent has complete control over what to do. Can either decide to go north, it can decide to go east, west, or south. But what it can't control is where it will finally land up. So for example, the environment could be stochastic. So if I choose to move north, I could end up in 6, 7, and 7, 8, or even in state 4 itself, right? So that depends on the environment. So that is not under the agent's control. What is under the agent's control is the policy, how to behave. That is under the agent's control.
Okay, okay.
Okay, any other questions?
Sir, in the last grid question, if you could come here, it is mentioned that the policy is deterministic. And so because of that, the value function we got was 0.0314. Right. So because we only the only possible way was like, because since it is deterministic, whatever is the arrow it is marked, the same direction is what the agent will move. So let's say I had a case where there is a 0.2% chance, 0.2 probability chance. Let's say the arrow is marked right, but the agent can move top or bottom of it. Okay, so
Okay.
then in that case, what will be the value function for the last question?
Okay, that's a bit tricky, right? You can't compute it. You can compute it. That's what we'll do next week. So we'll discuss how to find the value function for any policy, not just for deterministic policies, for any policy.
Okay,
So that requires you to solve a system of equations, right? We'll talk about that next week. But you can't compute it like what we did, right? Because the return will not be equal to the value function. Because once you enter probabilities into the picture, your expectation has to be taken into account, right? Value function is an expectation.
Yeah. Okay.
right? So you have to factor that. So it's not as simple as what we have for these two problems. I mean this problem.
Got. Okay. Cool.
Right? So that is all I had. Anything else? If not, we'll close the call. Is that fine? Shall we close the meeting?
Yeah.
Yes, sir.
Thanks,
Thank you.
Karthik.
Thank you.
Yeah. Thanks, Saikaran, and thanks, Varun, for joining. Thanks.